Welcome to The Explainer. Today, we are taking a deep dive into a really major breakthrough in how AI search agents manage their memory. We're looking at some absolutely fascinating new research out of the University of Illinois at Urbana-Champaign, UC Berkeley, and Chroma. They've just introduced something called Harness-1. It's a 20 billion parameter model that fundamentally changes how an AI interacts with the information it retrieves. So, if you've ever wondered how we can make AI systems just stop forgetting the vital clues they literally just found, well, you're in exactly the right place.
Okay, let's dive into this. Why do incredibly smart AI search agents suddenly forget what they just read? It's a highly relatable problem in modern AI, and honestly, it's essentially just a massive case of cognitive overload. You see, when an AI agent is tasked with researching a complex, multi-hop query, it issues searches, it reads documents, and it tries to piece things together. But traditional setups force the model to hold all that raw text in its active context window, juggling every single detail all at once.
And this creates what researchers call the append-only transcript problem. Think about it for a second. As the search transcript grows longer and longer, the AI is forced to be both the brilliant reasoning detective trying to solve the case and the disorganized filing cabinet desperately trying to hold on to every single scrap of paper. It's too much. Eventually, the model just collapses under the weight of its own search history. It loses track of which constraints are still open, which claims have actually been verified, and, what evidence is even useful anymore.
Section 1. The Agent Overload Problem.
And this brilliantly illustrates what goes wrong. Understanding this overload is absolutely key to appreciating the elegance of the new solution. When we train these models using reinforcement learning, we're currently forcing the policy, like the core intelligence of the model, to handle two vastly different jobs at the exact same time. It has to make high-level semantic decisions like what should I search for next, while simultaneously performing raw, tedious bookkeeping, like remembering document IDs and tracking whether a fact was in paragraph 2 or paragraph 10. That dual burden is incredibly inefficient. It completely consumes the model's optimization budget and makes learning highly unstable. So how do we fix this?
Section 2. Stateful Cognitive Offloading.
The researchers defined this new approach, and I'll quote them exactly here. A retrieval policy should make semantic decisions over explicit search state, what to search, which documents to keep, what claim to verify, and when to stop. The harness should maintain the recoverable state around those decisions. End quote. In other words, this gives reinforcement learning a stable, manageable interface for actually improving its search behavior, rather than wasting all its energy continually trying to rediscover its own bookkeeping from a giant wall of text.
Now, what's really interesting about this slide is how we can ground this complex architecture in a highly relatable analogy. Think of it as the brain versus the desk. The policy, well, that's the brain. It does the thinking, it makes the semantic decisions, analyzes the clues, and decides the very next move. The harness, on the other hand, is the desk. It handles the routine state management. It holds the folders, categorizes the files, and keeps the whole workspace perfectly tidy. By separating the brain from the desk, the AI can finally focus on actually solving the problem.
Section 3. Inside the harness.
Let's move to and see how this builds the overarching structure of the harness working memory. It's a total game changer. Instead of a messy, linear chat transcript, the AI is presented with a structured, budget-aware dashboard at every single turn. This is its working memory, rendering the exact state of the search operation continuously and clearly.
Think of these 6 components as the neatly organized drawers and folders of our researcher's desk. First up, the candidate pool. That's where all new search results land. Then the curated set, capped at 30 documents and tagged by importance, basically the AI's final answer pile. There's an evidence graph for connecting the dots, a verification cache that tracks which claims have been rigorously checked, a compression and deduplication system that filters out the noise and repeated sentences, and finally, an outer-tier full-text store that holds the complete documents whenever the brain really needs to dive deep. A super key feature here is the evidence graph. It instantly connects bridge entities across multiple documents. It maps an entity like Brussels or a specific date like 1878 to specific document IDs, like in this case, documents 22816 and 91442. This means the AI instantly knows which documents overlap on key facts. It changes a question from, let me reread my entire 10,000-word transcript to see what I know about Brussels, into a direct, instantaneous lookup right there in its working memory. It's huge.
Section 4. Generalizing to new tasks.
But we have to ask, does this structured workspace actually help the AI learn better, or is it just a neat trick for specific types of searches?
Well, when the researchers tested Harness-1 on completely held-out, unseen benchmarks, things like multi-hop QA and long context datasets, they found a massive 2.2 times transfer gap. So the crucial point is the model gained a massive 17 points in recall on tasks it had literally never seen before, compared to only a 7.9-point gain on its source family tasks. This proves Harness-1 performs exceptionally well on entirely foreign challenges. It's actually learning how to learn.
To really understand why, we look to this crucial quote from the study: "Operations transfer more naturally than domain-specific patterns stored in weights." Because the AI was trained to use a structured workspace, like how to refine a curated set, how to check an evidence graph, how to verify before promoting, it can apply those exact same logical operations to a legal patent, a financial SEC filing, or a complex web query. Organizing a model's workspace is just far more powerful than force-feeding it data and hoping it magically memorizes the right answers.
Section 5. David vs. Goliath Results.
Which brings us to the ultimate performance showdown. When stacking Harness-1 up against the competition, our 20 billion parameter underdog isn't just winning its weight class against other open source models. No, it is standing completely toe-to-toe with the undisputed, resource-heavy giants of the entire AI industry.
Check this out. It holds a massive 11.4-point lead over the next best open source subagent, Tongyi Deep Research. And get this, Tongyi actually has 10 billion more parameters. Harness-1 achieves this without a size advantage, entirely through the efficiency of stateful cognitive offloading. And that brings us to its final score, 0.730. To put that into perspective, this represents its stellar average curated recall across 8 incredibly diverse and highly challenging benchmarks. We're talking about scouring through complex corporate finance documents, deeply technical patent filings, and multi-hop web queries where the answer requires piecing together 3 completely different websites. Across all of it, it successfully identifies and curates the golden relevant evidence 73% of the time.
Look at these numbers. This plucky 20 billion parameter underdog beats GPT 5.4. It beats Sonnet 4.6. It beats Kimi K 2.5. Models with vastly more parameters, vastly more compute, and vastly more training data are straight up losing to Harness-1. Why? Simply because Harness-1 has a better organized memory. It doesn't have to spend its intelligence trying to remember where it put its files. It just reaches into the harness and finds them.
Which leaves us with a truly fascinating question to wrap up on. If a well-organized digital desk helps a lean 20 billion parameter model punch so far above its weight that it rivals the massive giants of the AI world, what exactly is going to happen when those massive frontier models are given this exact same harness? What will AI be capable of when it literally never forgets? Definitely something to think about. Thanks so much for joining me on this explainer, and keep learning.